All right, let's just dive right in. For more than a century, we've all heard these incredible ideas from modern physics, right? That time can literally slow down, mass can become infinite, and that for a little photon zipping along at the speed of light, time just stops. But what if those aren't profound truths about our universe? What if they're actually the result of a mathematical mistake made 100 years ago? Well, today, we're going to pull on that exact thread. So let's just kick things off with the big question, the one that probably bugged you in science class. If a photon experiences zero time, how does it get anywhere? How can it possibly travel from point A to point B? You know, this single question is our rabbit hole into a totally different way of looking at light, time, and, well, pretty much everything.
And to explore this, we're going to be looking at the work of a physicist named Miles Mathis. His big idea is that all these famous, mind-bending paradoxes in physics aren't some deep mysteries we just have to accept. Instead, he thinks they're like giant blinking signposts, pointing directly to fundamental errors in the original math.
Now, this is where it gets really interesting. Mathis basically argues that when your equations start spitting out impossible answers, like infinite mass or zero time, your first reaction shouldn't be to invent some wild new philosophy around it. It should be to go back and check your work. And he claims that's exactly what he did. So, to really get his argument about time, we have to start somewhere else first. We need to understand how he redefines the very thing that's supposedly not experiencing time, the photon itself. Because in his model, the photon is not at all what we've been told it is. So, in the standard physics textbook, a photon is basically a massless point. But Mathis says, nope, that's not it at all. He pictures the photon as a real physical particle. It has a tiny bit of mass, it has a radius, and its energy doesn't come from frequency, but from something he calls stacked spins. The idea is that photons have multiple spins all happening at once, and the more spins you stack on, the more energy the photon has.
And listen, this isn't just some vague concept. Because he treats the photon like a physical object, Mathis's model lets him actually calculate its properties. His papers give it a very, very small but very real mass, along with a specific energy, radius, and wavelength. These are all concrete numbers that come right out of his equations.
Now, this new definition leads to some pretty weird results. For example, we all learned that high-energy light, like UV light, has a short wavelength. Makes sense. But in Mathis's model, that whole relationship gets flipped on its head. High-energy photons, the ones with more of those stacked spins, actually have a larger wavelength. It's like the charts we're used to seeing are completely backwards. Okay, so let's follow the logic here. If a photon has mass, like Mathis says it does, then that opens up a whole new can of worms, right? Why does it always travel at one exact speed, c? Shouldn't we be able to, slow it down or speed it up a little? His answer is another really key idea in his work. Something he calls a universal charge field. He imagines this field as a kind of background sea of tiny particles filling up all of space. So photons are never really traveling in a perfect vacuum. Instead, he argues that it's their constant interaction with this field that locks in their speed. And he's got this great analogy to help us wrap our heads around it. He says thinking about this charge field is kind of like calculating the population density of a country. The weight or mass of each person isn't what matters for how crowded it is. It's their physical size. And he says it's the size of the photons moving through this field that really counts. So here's the kicker. He proposes this feedback loop. If a photon moves into an area where the charge field is a little denser, its own properties, including its mass, actually change to adapt. And this constant dynamic adaptation is what keeps its speed locked at c, no matter where it is. It's not some magic universal constant. It's the result of a physical equilibrium. Okay, so we've got this new and improved photon, it has mass, and it's moving through this charge field. With all that in mind, we can finally go back to that very first question we asked. Does time actually stop for light?
And Mathis really does not pull any punches on this one. He thinks the standard explanation, that velocity is only defined from an outside observer's perspective, is just a total dodge. He calls it philosophical misdirection, comparing it to a nonsensical riddle you'd get from some cool Zen boy sitting on a bamboo mat instead of a straight answer from a physicist.
He says the problem is just basic logic. We all learned this in middle school, right? Velocity equals distance divided by time. So what happens if the time is zero? You're dividing by zero. The whole equation just breaks. If time is zero, your velocity is mathematically undefined. You literally can't be moving. And this leads him to his main point, his central thesis. He states it as a simple, unavoidable fact. Motion and time are completely tied together.
if something is moving, it has to be experiencing time. So since we obviously know that photons travel, they must experience time. The idea that time stops for them isn't a paradox, he says, it's just a flat-out contradiction.
So, if the logic says time has to pass for a photon, but Einstein's equations say it stops, then something's got to give, right? Well, according to Mathis, the problem isn't with the logic, it's in the equations themselves. He claims to have found a very specific error in Einstein's original math.
Let's break down his claim. He points right to the source of all the weirdness, that famous gamma transform from Einstein, which has a square root in the denominator. That little square root is the villain of the story. It's what causes all the trouble at speed c, where you end up dividing by 0. Mathis says he found a fundamental mistake in how that equation was derived in the first place, and he corrected it. And the result? His new transform doesn't have a square root, and without it, poof, the paradoxes just vanish.
And the takeaway from all this is just huge. If he's right, it means that the most bizarre, mind-bending parts of relativity, infinite mass, time stopping, aren't actually deep features of our universe. They're just glitches, mathematical artifacts left over from a solvable error. In this model, they're not even real.
And that really leaves us with a final massive question. Whether Miles Mathis is right or completely wrong, his work makes you think about the process of science itself. When a theory is as rock solid and successful as relativity, what does it actually take for a different idea to even get a fair hearing? What's the burden of proof you need to challenge one of the absolute pillars of modern science? It's definitely something to think about.